Let's talk about limits of sequences. With limits I mean if you have a sequence an, then I'm really interested in what happens to the sequence if n is a big number, a really big number. Sometimes this is also called the long time behavior of a sequence. We will encounter basically two possibilities, which is convergence and divergence. Before I define them mathematically though, I would like to show you two examples. So let's look at this example. An is 2 divided by n squared. Again, the question is what happens if n becomes big, right? If n becomes big, then n squared is even bigger, and then 2 divided by n squared will be a very, very small number. And this is indeed what we see in the view graph here. So the first number is 2, then we get 1/2, then we get something like the 3, n squared is 9, so we get 2 divided by 9, etc. So this sequence seems to get closer and closer to 0. And in fact, we will later see that this is convergence, and we say this converges to 0. Let's look at the other example. So an is sine of n. We know the sine function oscillates between plus and minus 1. If I substitute integers, I still keep this oscillation in a weird fashion. So you see the dots, and they distribute themselves in a kind of a strange way. You have a few above the axis, you have a few below the axis. From this picture it does not look, you cannot decide if it converges or if it approximates any number. So here we have 15 iterates. What happens if we use 1,000 iterations? So here on the right I use 1,000 iterations, and you see the dots distribute themselves almost equally above the axis and below the axis. It doesn't seem to get closer to 0, it doesn't seem to get closer to any other number. You get these weird patterns inside, these kind of lines which appear. We are not discussing those right now. This needs some further investigation. However, for our purpose, I would just say it does not converge, so then we call it diverges. So these were two examples. So let's try a definition. How would we define this? So a sequence an, we say, has a limit, and we call the limit L, we give it a name. If we can make the terms an as close to L as we like by making n large. And in this case we write limit as n goes to infinity of an is equal to L. We have a second notation, but before I show the second notation, let's go back to the example where I say it converges. So here, here. So we said we can get as close to 0 as we want if we choose n large enough. And here it really looks like if we choose n even larger, we would get even closer to 0. Now the other notation which is sometimes used is an converges to L as n goes to infinity. So you find really both of these versions interchangeably in the literature, so you have to learn both. In this case we say an is convergent when the limit exists. If the limit L does not exist, then we call a sequence divergent. For does not exist, we sometimes use the DNE. You might have seen that elsewhere. So then we call it divergent. Now divergence can arise in many different ways, and we have seen a few ways already before. So one way would be, let me sketch this here. So if you have a sequence of values which really grows and grows and doesn't stop growing, so the an become very, very large, then we say the sequence diverges to infinity. So right here. In another case, if they become very, very negative, so maybe I plot this here, so the same thing can happen with negative numbers, right? Then they diverge to minus infinity, and actually here this must be diverge and not converge. And then there's a third case, like we have seen for the sine of n, which we have done earlier, that there doesn't seem to be any convergence to anything. It doesn't go to 0, it doesn't go to any other number, it also doesn't go to infinity or to minus infinity. So numbers are kind of all over the place. So divergence is a tricky thing, and it can arise in many different ways. Let's come back to convergence, and also convergence can be interesting. For example, the sequence here on the left, this is actually an is equal to n to the minus 1/2 times cosine of n divided by 30. So it's a little bit more complicated formula, but you see 1,000 iterations, and you have a very clear oscillation, which you kind of expect since the cosine is involved, but you do get closer and closer to 0. So this does converge to 0. So I can just write maybe an converges to 0 as n goes to infinity. Now this example is a little bit too complicated for the stage we are at now, so I cannot really prove that this goes to 0, but I show you anyways. For the other example which I have here, this is an is n divided by 2 plus 0.1 n square. Here I can actually prove that an goes to 0 as n goes to infinity, and I do this in one of the next slides. Here is interesting. Well, first of all, this does go to 0. This looks like it, no surprise here. Interesting is this bit, that you first have an increase. You have a very steep increase. The sequence becomes actually relatively large before it then eventually dives down, and then after a very long time it will approach 0. You can do all kind of computations, manipulations with a limit. So for example, if you have a sum of two sequences, so the limit of the combined sequence an plus bn is the sum of limit n goes to infinity an plus the limit as n goes to infinity of bn. Similar for the difference. If you have a difference of two sequences, then the limit is the difference of the limits. If you multiply a scalar like c, then the limit of can is c times limit as n goes to infinity an. And for a product, you can take out the limit as well. So the limit of an times bn is the same as the limit of an times the limit as n goes to infinity of bn. Now with fractions, it is almost the same. Limit n to infinity an divided by limit n goes to infinity bn. However, we need to assume that the denominator is not equal to 0. So this guy cannot be 0, otherwise we can't do this. We will do examples in a second where we use basically all of these rules, and you will see it is simple to use them. To see them together on this one slide, it looks maybe a little bit overwhelming, but you will get used to manipulation with limits very, very quickly. And you will see in the two next examples that this is actually not very difficult. So let's look at the example from before, and let's use these elementary computations to compute the limit. So here the sequence is again, an is n divided by 2 plus 0.1 times n square. And how do we compute the limit as n goes to infinity of this ratio? To compute this limit, we multiply the numerator and denominator with 1 divided by n squared, because n squared is the highest order of n that arises here. Okay, so what I do is I write again limit as n goes to infinity, and then I divide the numerator by n squared, and then the denominator by n squared. N squared divided by n squared. By the rules for fractions, these n square factors really cancel and you get the original fraction. But now let's compute this out. So this is limit as n goes to infinity. Here we keep a 1 divided by n, and in the denominator we get a 2 divided by n squared plus 0.1, and the n squared there cancels. Okay, now we use one of the rules for the limits. So the limit of a fraction is the fraction of the limits. That's what we use. So we write it very complicated first. Limit n goes to infinity, 1 divided by n, and then all this divided by limit n goes to infinity, 2 divided by n squared plus limit as n goes to infinity of 0.1. This is all in the denominator. But now we can take the limits. I'm running out of space, but this will be enough, because the upper limit as n goes to infinity, 1 over n will go to 0. Right? 1 over really, really big number goes to 0. as limit n goes to infinity 2 divided by n squared, this also goes to 0. This in fact was the very first example of the slides. This goes to 0. And as limit n goes to infinity of 0.1, this will be 0.1. So what we get is 0 divided by 0 plus 0.1. So we are not dividing by 0, which means the 0 in the numerator gives us the result. So the whole thing converges to 0, and this is what I claimed. Now, since this is so much fun, we do one more example. So let's compute this limit, again in the same method. So we look at the highest order, which is n squared here and n squared here. So we need to divide the numerator and the denominator by the same number. So this is limit as n goes to infinity 3n squared plus 8n plus 2 divided by n squared, and now comes a large fraction, and then minus 4 minus 5n squared divided by n squared. So let's compute this out, and it is important you always carry the limit until you finally do the limit. But if you keep n in your equations, you carry over the limit sign. So the first term is a 3, then we get plus 8 divided by n, and then we get a plus 2 divided by n squared, divided by, and this is a 4 divided by n squared minus 5. And now we use one of the limit rules for fractions. So then this is the limit as n goes to infinity of 3 plus the limit as n goes to infinity of 8 divided by n plus the limit as n goes to infinity 2 divided by n squared. I know it gets a little bit boring, but we have to do it properly at least once in our life. So limit n goes to infinity 4 divided by n squared plus limit as n goes to infinity of 5. And here I made a mistake. This must actually be a minus. So now I'm in a position where I really can do the limits. Wonderful. So things get easier. So limit of 3 is 3. There's no n in there. The limit of 8 divided by n goes to 0 because n becomes really, really large. So this is 0. Plus the limit 2 divided by n squared, which also goes to 0. So this is gone. In the denominator, we have a limit 4 divided by n, which goes to 0. And then we have a limit of 5, which is 5. So all of a sudden, we come up with a very nice number, minus 3/5. And this is our limit. So we could compute the limit of this very complicated expression here. Let's look at a view graph of this. So here's our computation, which we just did. And here's a graph of the same sequence. You see the ANs, actually it's funny, the first expression is 1/2, which is positive, but then it jumps down very quickly to a negative number. And then it stays negative, but here it seems to kind of converge to a certain value, and in fact this is minus 3/5, as we just computed. So the computation works really nicely. Let me summarize. So sequences can be convergent or divergent. For convergence, we introduce the notation limit n goes to infinity an equals to L. So we have a number L which gives the limit. The limit respects addition, subtraction, multiplication and division as long as we do not divide by 0. Yes? Yes. Oh, I think Tolo wants to talk to me. What's up, Tolo? What do you mean you are divergent? Oh, your intellect has no limit. Right.